Hi everybody, this is part 2 of our video lecture series for AI. I'm Marty Geyer, your professor, and I wanted to give everybody an opportunity again to learn a little bit about iterative depth first search. Fortunately, it doesn't all fit on this little whiteboard, so you'll excuse the tiny writing. I'm well aware of what you can see and can't see because I ran a quick test, so I promise I'll read everything off. I'm also trying to do the video kind of without video editing software, so it sucks, really, but I should buy some. But I haven't done that yet. So trying to get this up quick and dirty for you, especially on Sunday, right before things are due, to try to help you out at the last second, especially if you're panicking and worrying about all this stuff. So this is iterative depth first search. Again, what we have here is a 15 puzzle, which is a 4x4 board, and a puzzle, 3x3 board, and what we're going to do on this lecture is we're going to cheat and use a 2x2 board with a 3 puzzle because it's easier to explain and because it's a nice easy abstraction and you can go up to a 4 puzzle pretty easily from it. So what we have here is a random board state for 4 puzzle, which consists of blank 3, 2, 1. The solve state for the 2x2 puzzle for 4 puzzle is, of course, 1, 2, 3, and then a blank at the end. Now what I'm going to show you is how to work through the iterative depth first search, and then I'm going to show you a little bit of the algorithm to help you get started. Now I want you guys to be in the habit of being able to take an explanation like we're doing here and or reading explanation from the book and turn it into an algorithm yourself. Not the algorithm, I'm sorry, but turn it into code yourself. So I'm going a little bit lower level than I otherwise would. Next week and weeks after, I kind of want you to do a little more, so you'll see a little less of the actual algorithm in code form that you have to kind of figure out how to do. But I'll hit the main points, so you definitely will have enough information to go forward. And of course, you can always ask the questions. All right, enough with the pleasantries. Let's get started. So again, random board state -3, 2, 1 is what we're going to start with because it's a nice simple example. And what iterative depth first search does is it doesn't use any intelligence whatsoever. It also doesn't use any save states. This is important. So breadth first search does save states. You keep track of where you've been so you don't accidentally go there again. Depth first search doesn't care. That's a problem because it can loop forever, of course. Notice particularly in this puzzle, when you go from one state to the next, you can always go back. And in fact, there are only 2 moves in each of these states for this puzzle. On the 4x4 puzzle, there's of course 2 moves in the corners, 4 moves in the middle, and 3 moves most places. So there's always a move to go back to your previous state. You don't want to do that. But for iterative depth first search, we actually don't care because we're just going to do that again and waste that time. That's why it's not a perfect algorithm, but we also don't have to worry about coding all those pieces to check, and you don't have to worry about the memory. Because when you're searching bazillions of states, that memory is going to be the first thing that's going to go out on you. It's going to be a problem for A star, particularly for breadth first search, if you have to search a lot of levels. So this takes that problem away, at least. So when you go from this random state, say, to this first state here, which is 3-2-1, we just move the dash over 1, you can always go back. Now notice, well, I'm getting ahead of myself, let me back up. So first thing you need to do, as with any of these algorithms, is have a board and generate successor states. Successor states refers to the states coming off after the possible next states from this state. So you can move the dash over here or over there. This state down here is represented by moving it over 1. So we have 3-2-1, and this state over here, which I keep blocking, but I'll try to show it for a second, is moving the dash down, which is 2-3-1. Now, we don't really pick one state over the other, we just simply pick one at random, which is easiest to code if you think about it in terms of just pick the first one. So what we're going to do is just pick the first one. So this is the first one we did, just because that's the way it came out, no particular rhyme or reason. So we're going to pick this state. We're going to change to this state. Most of you have in your algorithms now code that switches from one state to another because you had to do that kind of in the first week in order for a user to move. So switch to this state, and now we're going to check if that's the solution. It's not the solution, right? So we're going to do the same thing again, generate all the states. Now, again, notice in a 4x4 puzzle, you'd have lots of states here. You have several branches. Here you only have one branch. You either go back or you go down 1. On the 4x4 puzzle, you'll have 1, 2, possibly 3 branches on the bottom, or possibly just the 1, and then 1 going back up. You treat that 1 going back up as just another successor state. So kind of visually they're represented here, but this is the root node, and these are the two leaf nodes off of it. Don't worry about the fact that it's going back up, because again, we're not going to keep track of that. We're just going to waste that time. So we might actually, let's say, for argument's sake, have generated this state first in our algorithm that randomly generates all the next states. And that's the worst case, because we just went back. But let's do it anyway. So we went starting again from here, went down to here. Now we're generating two states, this one and this one. We just pick the first one, let's say it's this one again. So we go back up here. Now you notice we can just loop back and forth and back and forth, but the iterative depth first search will stop us after the maximum depth is reached. Now the other piece of this puzzle, for depth first search, it just keeps going. The other piece of this puzzle is you have a iterating depth. So you start at 0. This is depth 0. This is our first random state puzzle, -321. And this is depth 0. This is no state or no depth under this has been generated. We're just doing this initial state, and we check to see if it's solved. So in the algorithm, we're actually going to start with a depth 1, but the generative case is just 0. And the first 0th depth, you just check if it's solution. If it's not, then you're done. You can't do any more on this depth. So you increase your depth to 1. Depth 1, now you generate the next two states, which is this one and this one. You go down to this state, at random again. You see that it's not the solution. Now you've reached your maximum depth, so you don't go down any further. Now you go pop back up, and you go to the next one. The next one, also not a solution, and you reach your depth, so you go back up. And now you have no other states, and you've reached your depth everywhere, so you're done. And this failed. And then you have to increase your depth again. So again, now we're at depth 2. Depth 2, we go down to here. And then let's say we again pick this state back up here because we're stupid. We go 1, 2. We reach the depth. It's not the solution. Done. So we come back up. But now we go to this state's other state. So this is one of the successors. This is the other one. We go here. We see that it's not the solution. We're at depth 2, which is our maximum. We're done. We go back up. We go back up. Now we go back to the second state here because that has been exhausted at X depth 2. Go to this one here and generate its two successor states, which is again this one here and this one here. And you just pick one random again. Let's say this time we happen to pick this one. Go down here. It's not a solution. Go back up. Pick its next state, which is this one. It's not a solution. Go back up. We have no more nodes. Everything has reached its max depth. We go back up again. And now there's no more nodes here. Everything has reached its max depth. Now we're done. This depth failed. Then we iterate to depth 3. And it kind of goes on in that fashion. I think you can see the general idea now. Now, notice eventually you'll get to the solution if one exists, because you'll just keep going and going and going. But notice you do a lot of this wasted state stuff. So, at depth 6, for example, one of your states is you're going to go from here to here to here to here to here, and that's absolutely ridiculous. Don't worry about it. It's fine. It's a computer. We waste its time all the time. That's really the answer. So it's fine to go back and forth, back and forth, back and forth. You're going to waste that line of reasoning and go back all the way up. But then you'll eventually find the actual path solution through, which if you'll notice, by the way, is down this path here. When you go here, here, and a couple more states down, you actually get to the solution here. I believe it's at depth, let's see, 1, 2, 3, and then you want to move the 3 down there, and then a 2 over there, and then 1 down there. So 3 more depth paths, so it should be at depth 5. You find the solution down here, but you'll have wasted all this other processing power. Notice also you keep going through the same states again. When you were at depth 1, you already looked at these things. Now you're going to look at them again at depth 2, again at depth 3, again at depth 4, and you're going to repeat all that work. So it's a lot of wasted resource time. And that's why we can improve on this on the other algorithms. But for the purposes of this quick and dirty algorithm, it doesn't use a lot of memory. It relies on speed and just being able to find the solution eventually. And if those assumptions fail, then you just won't find the solution. This is a big puzzle. You may not actually find a solution, especially if you start in a random board state. It might be far enough down that you've exhausted the space on the stack and you just blow up the whole algorithm running before you actually find a solution. That's possible. So when you're testing, you want to make sure you generate a bunch of random states. That way you can be sure, well, you can be more reasonably sure that you've picked one that does have a solution, because eventually, randomly, statistically, you'll pick one that has a reasonably depth solution that your algorithm can get to if it works correctly. I'm going to stop it here, and in the next video we're going to go through the algorithm itself, and I'm going to show you how to do that.